Hi, everybody. So today we'll be talking about Ethereum and smart contracts. And just for a quick introduction, I'm Janice. I'm currently the head of education. I've been doing a lot of behind the scenes for this webinar, and I'm really glad to have all of you guys come out to participate in our lectures. And we also have Saneel. Saneel, do you want to give a quick intro?
Yeah, sure. Hey guys, I'm Saneel. I'm a software developer with blockchain at Berkeley. I also spend a lot of time in the crypto space. I'm currently working over at Polychain Capital, where I do a lot of deep research into kind of emerging fields in this space. So quite excited to teach you guys about Ethereum and smart contracts.
Great. All right, so this is our table of contents today. First, we'll be going over smart contracts, then Ethereum virtual machines, and then use cases. So I'll be taking over the first half, and then Sunil will take over later. So let's begin. So we'll be talking about smart contracts. But before we start, let's have a little recap. What makes Bitcoin so special? So you can type it out in the chat, or you can just have a little, reflection in your mind for 5 seconds before I spoil it. Okay, well, hopefully you had to think about it. But basically, it's because of Bitcoin's bare bones, right? It's cryptographic identities and how it uses a record-keeping kind of structure and a trustless consensus. So let's kind of dive into that world right now. And this is kind of a review from before. So as we've talked about many, many times, the benefits of Bitcoin include that it's pseudonymous, which means that when we talk about, Bitcoin, it's emphasized the importance of identity, and especially in order to enable authentication and integrity. So we use cryptographic identities that allows for accountability. It gives everyone a unique identity through a hash. And we've gone through this in lecture 2, right? Bitcoin uses SHA-256. And this generates a private key and a public facing address, which is your public key. Secondly, it's democratic, which means decisions are made through a consensus protocol. It doesn't require you to trust anybody else on the network. You just really need to trust the math behind the consensus. Thirdly, it's immutable, of course. Everyone sees the same version of the truth since we have consensus. This makes it also temper evident because of its data structure so that no one can really change the history. But if someone does, we can easily see it that it has been changed by using the Merkle tree and comparing the hashes, right? Fourthly, it's uncensorable. To censor the transactions, you need to control a large proportion of the network, which is not easy, as we talked about before, and it cannot be controlled by any one party since it's decentralized, right? It's distributed, which brings up to the next point. There's no central point of failure. The execution of transaction really depends on a network of miners located around the world. So as we talk about Ethereum and smart contracts, let's keep Bitcoin's architecture in mind. All right, so first, before we dive into smart contracts, let's just all, come to consensus on what a traditional contract is. The dictionary states, a contract is a written or spoken agreement that is intended to be enforceable by law. Notice, the contract must be agreed upon and enforced by law, right? Thus, a consensus protocol is needed. Through a consensus, we should all be able to agree on both the contents of the contract and the execution of the contract, right? But what makes a smart contract smart? So a smart contract is a piece of code that facilitates, verifies, or enforces the negotiation or execution of a digital contract. So to reach consensus, a trusted entity basically must run this code. And we all need to trust that a digital contract is enforced correctly. So the key difference from a traditional and a smart contract is the execution and the enforcement, which is done through algorithms instead of law or like a third party. Hopefully that makes sense. All right, so now that we have the basics of what a smart contract is, let's move into Ethereum. So what is Ethereum? On its website, it states that Ethereum is a decentralized platform designed to run smart contracts. And now we know what a smart contract is, right? So basically, it's a distributed computer spread amongst a multitude of nodes across the world that executes code that people feed into it. And because of this architecture, it can run many, many applications. The execution of transactions bring us from like a previous state to a new state, which is also called the state transition function. And like and in Ethereum, it has a native asset, which is a type of cryptocurrency, and its value in the Ethereum ecosystem, which is the Ether. And it's crucial in aligning incentives, which we'll dive into more later. And if you're wondering who is on the right in the photo, that's me and Vitalik. Vitalik is the founder of Ethereum, and that was a great day that I got to meet him. So a little bit of information about Ethereum. So the block creation time compared to Bitcoin is Ethereum takes 13 seconds, whereas Bitcoin takes 10 minutes. So you can see that significant difference. And currently the exchange rate, though I think it has went up in the past few days, is 367.75 USD for 1 Ether. And you can just check this out on the internet, and you can just search it up. And the graph below just shows Ethereum's average block time and how it kind of like fluctuates, but has been decreasing in these past years since 2016. All right. Okay, so in order to understand Ethereum a bit more, let's compare it to something that you know pretty well already, which is Bitcoin. So like we mentioned a few slides before, Bitcoin is special because of, it's because of the following. It's the first successful cryptocurrency. It's trustless, it's immutable, it's uncensorable, it's pseudonymous, and there's no central point of failure. And it's one CPU equals one vote, right? That's just a little bit of a review for Bitcoin. And so what's the difference in Ethereum? Well, Ethereum has all of these, but it has a different use case, which is what we'll get into right now. So Ethereum and Bitcoin are currently the two most popular blockchain platforms with two different goals. First, Bitcoin. So Bitcoin is like the gold standard of blockchains. It has been around for the longest and had successfully supported many, many number of transactions. It's simple and robust. It's UTXO account based. It's not Turing complete, which means that, it can't have a loop. And the main purpose is to allow the transactions of Bitcoins, right? That's what Bitcoin does. Whereas in Ethereum, it's a smart contract blockchain platform. It's basically a distributed world computer. And the asset is Ether, which is used to, fund computations and also align incentives. And the main purpose of Ethereum is to not be like a global payment system only and to only do transactions of Ether. It supports more features like running decentralized apps on Ethereum and many, many programs. And just a little comparison, Bitcoin is stack-based primitive scripting language, which means it's not Turing complete, as I said, and it makes applications on Bitcoin more limited. Whereas Ethereum uses Turing complete, which you're able to write a loop, and many more applications are able to be developed, and it's more developer friendly. Okay, so now let's compare the accounts of, a Bitcoin account and types of Ethereum accounts. So the difference is that Bitcoin is a UTXO base, whereas Ethereum is account based. So in Bitcoin, private keys prove the ownership of a UTXO. When you spend Bitcoin, you spend from a previous transaction, right? And to calculate the current balance, you have to sum up all the UTXO that you own. Hopefully you remember the piggy bank analogy. So, when you spend a specific amount of Bitcoin, you break open that piggy bank, take out how much you need, transfer it, and then the rest, if you have any remaining Bitcoin, goes to a new piggy bank, right? So this makes it easy to make transactions and prevent double spending, right? But in Ethereum, we don't use the UTXO-based model. So private keys prove ownership of an account instead, and it tracks a current balance. So this is more space efficient than UTXO, as when calculating your own balance, you just reference to your own account. And it's stored next to the address in the state, and you only need to access your Ethereum wallet. So using this account-based model, it's much cheaper and it's easier to look up the account balance, right? And you just transfer between accounts when we have an account model. All right. So in Ethereum, there's two types of accounts. There's externally owned accounts and there's contract accounts. So first, externally owned accounts basically contain an address that they use to let people send them Ether and also a balance of Ether. And it's owned by an external entity, and you're able to send transactions to transfer or trigger a contract code. Secondly, we have contract accounts, which is owned by a contract. It's basically code. It contains an address associated with contract and persistent storage. And the code is basically executed when externally owned accounts or other contract accounts make transactions to trigger their code's function calls. So those are the two account types in Ethereum. Okay, so a little bit more on smart contracts and its control. So smart contracts are like autonomous agents that live inside of Ethereum network. It reacts to the external world when they're poked or called by a transaction, which calls specific functions in it. And it has direct control over, the internal ether balance, the internal contract contract state, and the permanent storage. So why would you use smart contracts? Like, why do people use it? So here are some purposes that, I believe Ethereum serves. So it serves four purposes, I think. First, it stores and maintains data. The data representing something useful to users in other contracts. For example, it could be a smart contract defining a new token currency or an organization's membership, which you have to pay a certain amount to obtain. Secondly, smart contracts can be used to manage a contract or a relationship between untrusting users. For example, like insurance companies or financial contracts, or even between you and your landlord on rent. That can be on a smart contract too. Thirdly, it provides additional functionality to other contracts. You can write contracts that calls other functions, perhaps using their software library, and you can leverage the functionality of an existing contract. And fourth, smart contracts can be used for complex authentication use cases. And Saneel will talk more about these use cases in a bit, so don't worry about that. Okay, so a little bit of recap again. So the recipe for mining in Ethereum is, first you have to download the entire Ethereum blockchain and then verify incoming transactions and run smart contracts code invoked by transactions. Then you create a block and you find a valid nonce and you broadcast your block and then basically profit. It's quite similar to Bitcoin's recipe for mining with a little bit of changes if you can deduct them. All right, so just to summarize again, Ethereum is a distributed computer, which means that every node executes Ethereum smart contracts, then come to a consensus on a new network state, right? The state transition function. And Ethereum's distributed consensus protocol is currently proof of work. Miners competitively create blocks by executing code and searching for a solution to the mining puzzle. And the network consensus basically removes the need for trusted third parties, right? And any violation of contracts requires subverting the entire network. And it's secure peer-to-peer agreements that live on the blockchain forever. So now Saneel's gonna hop in real quick to talk about, to break this down for you. So Saneel, do you wanna hop on?
Yep. Hey guys. So I'm just gonna break down this kind of contract here really quick. So there's a few components of a contract, right? But the one thing to really understand is that contracts are kind of managing interactions between people on the blockchain, right? So when we say there's an address, right? If we specify, so this entire thing is a contract, hence the kind of data structure indicating that. If we specify that there's an address, right? That's just referring to kind of what you would expect, right? An Ethereum address that usually belongs to some kind of other user. And then we have a struct, which is another kind of unique thing to Solidity in terms of defining a contract. A struct you can think of as a sort of wrapper for more complex information. So, if this struct here is a bet, right? So I may want to store information about a bet, right? So, an outcome maybe like 1 or 0 to say if it paid off or it didn't. the amount that I kind of betted on, right? And then whether or not I've actually placed the bet. So I can wrap that up into a struct and I can use that later on in my contract. Mappings you can think of similar to kind of dictionaries in that they have sort of a key, so like a way you identify a piece of information, and then kind of what that unique piece of what that key maps to in terms of this unique piece of information. So address to bets mapping would be like I have a bunch of different Ethereum address, and then I have the bet information that that address placed, and then winnings in the same sense, kind of the amount that each address won. And then these functions that you see here are kind of where we define the kind of logic for a contract. So while this is all just defining how we actually store and deal with data, these would be kind of the functions that actually decide how that data is actually used and manipulated and reflected across the state. So when we have a payable function, that usually means that there's going to be some sort of exchange of money or on-flow assets, right? And it's just kind of a thing that we use to specify that this function is actually dealing with the transfer of value, right? An oracle only, sometimes contracts refer to external oracles. They're called oracles because they kind of provide information that you wouldn't be able to find otherwise on chain. So this could be like an external API. It could be something else, anything that's licensed to kind of go provide information on chain. And when it says oracle only, this decision will only take in data from that oracle and then follow some sort of computer logic. Yeah, so when we say here, we'll define kind of what you need to put in. So in the make bet, you would need to put in kind of like the outcome, so like how much you're betting and whatnot, and then it would return whether or not it's initialized, so a boolean, so true or false. Yeah, so that's kind of this general purpose. Yeah.
All right, thank you so much, Saneel. Thanks for hopping in. He's a software developer here, so thank you. All right, so let's move on to Ethereum virtual machines. And if you have any questions, please feel free to use the Q&A chat box in Zoom. Yeah, and we'll answer it right away. Okay, so let's enter the world of Ethereum virtual machines. Okay, so Ethereum smart contracts are generally written in high-level programming languages. So in Ethereum, it's Solidity and Viper are the two most commonly used languages that write smart contracts on Ethereum. So Solidity is a mix between C++ and JavaScript, whereas Viper is more Python-like. And smart contracts are written in these languages and are compiled down to EVM code. Or you can think about this as like a machine language. So it translates from a human readable language, so what we write in, through a compiler to a simple language for a machine to understand and execute, basically. All right. So let's have a little high overview of this. So the EVM is basically a mini computer on your computer that runs contract code. So miners in Ethereum creates blocks by executing EVM code and search for a solution to a mining puzzle. And every Ethereum node runs EVM. All right, so a little question, maybe take 10 seconds to think about this. What if our contract has an infinite loop, since it is Turing complete, right? So maybe think about that. You can write on the chat if you're not shy. Give it 10 seconds. Okay, all right. Hopefully you thought about it. So if our contract has an infinite loop, right, every node will be stuck executing the loop forever. And by the halting problem, it is impossible to determine ahead of time whether the contract will terminate or not. And this is a problem because it allows an easy way for attackers to launch a denial of service attacks, which is also called DOS attacks. And these attacks are basically, trapping computers around the world in an infinite loop, and you're unable to actually execute any meaningful contracts. So is there a solution to this? Hopefully, right? So the solution is gas in Ethereum, gas and fees. So a gas is basically what fuels the execution of a given contract. It's what you pay in the network in order for your transaction to go through. Transaction fees in Bitcoin are basically equivalent to the gas in Ethereum. And every Ethereum EVM operation code requires some gas in order to execute, and this prevents infinite loops and any attacks. And every transaction specifies a start gas, which is the maximum quality of gas it is willing to consume, and also a gas price, which is the fee in Ether it is willing to pay per unit gas. All right. So let's just hop right into the steps. So at the start of transaction, you calculate the start gas multiplied by the gas price, which basically represents the amount of Ether paid for a computation. And this is subtracted from the sender's account. And the sender is the one who invokes the contract by sending the transaction out. And if the contract is successfully executed, the remaining gas is refunded to the sender, right? So if the contract execution runs out of gas before it finishes, the execution reverts. The Ether has been paid, it's not refunded, and you might be wondering like why. So the reason why is that although the contract execution, gets reverted, has not been done, someone on the network actually put computational power to execute this EVM code of yours. And once the gas is spent up, it's proof that someone executed the program, and thus it's not refunded. So there's two end states. It's when one, the program terminates, or it runs out of gas. So even though Ethereum still allows someone to write an infinite loop, the attacker attempting to, DOS the network has to pay enough Ether to fund the attack. And purchasing gas is how basically the price you have to pay to use the distributed computational power. And this basically disincentivizes users from running expensive computations without having sufficient funds. So attackers will probably not attack, as it will cost attackers a large amount of Ether. It really depends which attack you're talking about, but this is what de-incentivizes it. Okay, so a little bit about state transition function. We kind of talked about it. So when we execute a transaction, we go from a previous state to a new state. At the beginning, there was a blank Genesis state upon which many transactions were executed like after. At any point in time, the final state represents the current state of the Ethereum. So at the start, we have the current block state, we have the gas required, we have the current memory, we have the transaction that's calling a contract, we have a message which contains like transactions metadata and so on. It's basically everything you need to correctly execute a transaction. You feed this into the EVM and you get out a new block state with all the updated account balances, the states, the new gas value, the gas or like the fund that has been refunded, and so on. All right. So some conclusions about Ethereum as we wrap up. The main goal is not to optimize computational efficiency in Ethereum, but it's to enable a distributed and trustless computation. So every node on the network has to run the same computations. It's redundantly parallel, which means that, we're doing the same things on different computers. The contract executions are redundantly replicated across all nodes, as I said, and the execution is very expensive actually, and it's memory intensive and it's slow. And you have to remember that, it's not supposed to be efficient. It's not supposed to be a way for us to reach, it's supposed to be a way for us to reach consensus among all parties and basically have a trustworthy output of the code. So keep that in mind. It's not supposed to be efficient. All right, so just to conclude, when you would want to use blockchain and when you would like to use a centralized database instead. And we use centralized database for a lot of things. So when would you use a blockchain? So you use it when you need, you need it for a shared database with multiple writers. And it's with parties you can't really trust, and there's no trusted third party or authority. And you're also interested in, fault tolerance, data immutability, or censorship like resistance. So that's when you would use a blockchain. Whereas a centralized database can be used for many things, like, you can use it when when it does not need to be shared or shared by parties you don't trust. And you must keep like the data confidential. And if you want to handle complex or large amounts of data, right, it's not efficient again, then you would like to use a centralized database. And if you need to edit your data, of course, you wouldn't want to use a blockchain for that. And then if you're interested in cost effectiveness, speed, or efficiency, a centralized database would probably be a better option. All right, so that's the end of Ethereum and smart contracts. If any questions about the content I just spoke about, just put in the Q&A and I'll answer it as soon as possible. And now let's move on to use cases with Saneel. Thank you.
Hey guys, yeah. So, given all that you've learned about Ethereum and EVM, I think now it's time to kind of delve into how this actually plays out in the real world in terms of developers building out applications on the virtual machine. So, Janice next. Yeah. So first, I'm going to cover some basic use cases. Yeah, you can go next. So one thing that's really interesting that you can do, kind of using smart contract functionality, is to create tokens on top of Ethereum. So obviously, Ethereum has its base network token, ETH, right, which is used to kind of pay for transactions done on the network. It's used as kind of the reward system for miners that create new blocks. But you can actually create tokens on top of these that are completely defined by software, and these are typically referred to kind of as programmable money, right? So the kind of thing that we like to say is you can pretty much recreate Bitcoin in 4 lines of code. And the way you do this is you basically can just create like a smart contract with one operation, right? A database with an operation where you allow a user to send to another user. You ensure that, we'll say Alice and Bob, Alice has enough money in her balance linked to her account and that she initiated the transaction, then she sends that to Bob. So this function here is a little kind of example of what that would look like. In terms of proper ERC20 tokens, there's actually a complex set of standards for this that actually define a set of functions that you need to implement for an Ethereum ERC20 token to be considered like a token built on top of that network. But one interesting thing we've seen with these tokens is that you can pretty much give them like really complex functionality. So this is a little bit of into the stereotype of where people might think it's like, oh wow, it's magic internet money, because realistically this is money that can be programmed, right? So an example of this is Ampleforth, which is an interesting token where if they basically program that token on top of Ethereum where you may have like 5 Ampleforth and they're all worth $1. Say that the price of Ampleforth raises to like $3, right? So now you have 5 Ampleforth worth $3 each, right? The next day, after a 24-hour period, you now have $15 worth of Ampleforth. So it actually changes the supply. So now you have 15 Ampleforth, each worth $1. So the idea is that when you have a lot of kind of like high volume and the currency is kind of less stable and like the price isn't changing a lot, it's always kind of worth $1. And that's just like one example of ways that kind of tokens on Ethereum can be implemented. So yeah. Another one is a DNS. So for those of you who don't know, the domain naming system is kind of it's a complex system that we have that kind of underlines the internet. But its core function is basically to map a domain name to IP address, right? So like when I go to like blockchain.berkeley.edu, that domain name maps to a server address, an IP address held by Berkeley or whatever infrastructure that BAB uses. So when someone goes and searches that up in their browser, it'll actually kind of make a query to the domain naming system. It'll take you to that IP address and then display the contents held there. So yeah, so this is an example, right? Yulin Chu maps to 1, 2, 3, 4, 5, 6, 7, 8. This is again really easy to implement in Ethereum. All we do is we have kind of that struct I talked about, where it's we will map like a string or something, or like an address to like we'll map it to like an IP address. Obviously, in real implementation, it would be a little bit more complex in terms of how you manage that. But once you kind of have that data storage and that structure that maps one value to the other, you then get a really simple function where you just put in a name, put in a value. You check if it's already in that stored in the contract, right? It's monitored there. And if it isn't, then you just assign that value, that IP address, to that name. So this is kind of a way in which we can like actually go and like, this is why like structs and contracts are useful, because you can actually track ownership associated with the name within the contract, and that gets reflected within the state. All right, yeah. So please feel free to drop any questions in chat. But now I think those are kind of very simple use cases. Now we'll kind of go into a more high-level overview of some more advanced use cases, and perhaps ones that are actually kind of very directly applicable in terms of these are use cases we are seeing built out and have attracted billions of dollars. So one, and probably the really hot one that maybe a lot of people have heard of is DeFi, or decentralized finance. So there's a tradition with kind of traditional finance, right? And when I say traditional finance, I mean kind of, stocks, bonds, our regular banking system, and whatnot. Which is that most of traditional finance, for one, is close to regular users. As an end user yourself, you can pretty much only go, or even as a university student, most of the time you can only go open like a bank account, maybe open like a Robinhood or like another brokerage account. But then there's like loopholes you have to jump through to get to even trading something as simple as like options, right? So that's one, right? It's pretty closed off to the average user. And two, most derivatives built on crypto, so derivatives built on like the movements of cryptocurrencies. So this is like an option on a cryptocurrency, right? The right to buy or sell at a certain point at a certain date in the future, are in centralized exchanges. So we actually don't. So if I wanted to go like get an option on Ethereum price, I'd actually have to go to Binance, where they'll issue that to me themselves, and again then I kind of have to trust Binance is going to like uphold that and like actually take care of everything on the back end, which is a little bit antithetical to the whole point of having crypto, right? We don't want to rely on centralized institutions that much. And then there's a few pitfalls with traditional finance. One, financial institutions can manipulate markets. We saw this pretty clearly in 2008, where essentially what a lot of big banks would do was they would kind of tip off ratings agencies to take a bunch of debt that was really, really bad. So, they knew that it was very risky and likely that that debt wouldn't get paid back, and say that that debt was a lot safer than it was, just so they could sell it to other people, right? And make some money off the commission of that sale. So obviously that ended up leading to like this kind of huge implosion in both the real estate market and the debt market and everything else. So one, we kind of want to avoid that. That 2009 was actually the date of Bitcoin's first Genesis block, which explains kind of its conception. So this led to a lot of mistrust in big banks and big institutions as a whole. And then finally, retail users are often like very much priced out. This is a little bit of an issue in DeFi as well, but most of the time not as big. So there's a solution of this that we built on Ethereum using smart contracts to handle logic, right? So the fundamental underpinning of this is that we can use game theory and economics to find ways to kind of cut on trust, right? To make a financial system where this is kind of trustless, and we don't need to rely on like these big centralized institutions to go verify transactions or go build out derivatives, right? And one an example of this, right? So I've displayed a few logos here. Usually, if I wanted to go exchange my cryptocurrency before this was kind of built out, I would have to go to something like Coinbase or Binance, and I would have to trust them and say, hey, okay, hold my cryptocurrency for me. And if I want to sell it, I'm going to tell you you need to sell that, and you're going to find someone that wants to buy it, right? Great, works well, especially a lot of large institutions that are just looking to trade it and don't care too much about things. But Coinbase actually just went down, I think today or yesterday. Binance obviously has been kind of attacked before. We've seen kind of a lot of exchanges like BitMEX got hacked and people have lost their money. So if there's a way to keep this exchange on chain, that would be great. So an example of where we do this is Uniswap, which uses kind of an automated market maker. And that's really fancy for saying it uses kind of a function that computes the exchange price between two pairs of assets. So instead of having a central person that will kind of match buy and sell orders for cryptocurrencies, what we have is we'll get a bunch of users. They'll own like a little bit of each token. So let's say I want to exchange Ethereum for Bitcoin, right? In Ethereum, you can't actually have like Bitcoin itself on it because it's a different blockchain, but we can wrap it and basically like say, okay, trust that a lot of this Bitcoin is held in like another address, and that address will issue a digital token on chain, right? So we have Ethereum and Bitcoin, right, on chain. Instead of going to Binance and like saying, okay, I want to sell this much ETH for this much BTC, what we'll have is we'll have these people come. They'll have a little bit of Bitcoin and Ethereum each. They'll put it into one of the Uniswap pools. We call them liquidity pools. And let's say the percentage is 50-50, right? So they'll put like 50% value in ETH, 50% value in Uniswap, and then people just go and call the smart contract to they'll exchange ETH to go into the pool to take out Bitcoin or vice versa. And then the price is dependent on kind of the proportion in the pool. So we have a lot of kind of advanced kind of apps now built out. We have everything from kind of lending, which is Compound, where you can go again put your money in one of these pools and people can come borrow, and then you'll get the kind of interest rate back. We have Open, which is actually started by Blockchain at Berkeley alumni. three of them in fact, and they kind of issue options on chain using a very similar thing. And then we even have Yearn, which kind of got a lot of attention in recent thing for kind of being a on-chain hedge fund, where you could go and deposit your thing and it would algorithmically go and try and find the best yield on your assets or the best returns. There are some drawbacks to decentralized finance. Again, I know this kind of hooks a lot of thing, and these drawbacks are kind of very in the intricate details of like how these protocols work. But at a high level, right, a lot of them are very capital inefficient. And what this means is if I want to go create like a derivative, right, or if I want to go and no, even better example is if I want to go and take out a loan on Compound, right, what that entails is I actually have to go put down more money in some other asset than the loan I'm taking out in my target asset, so the loan I want the or the currency I want the actual loan in. And obviously that's kind of sucks, right? Because you don't want to be kind of like putting up a collateral more than you're borrowing, but it's kind of necessary at this point for two reasons. One, a lot of currencies are still volatile, right? So depending on kind of the price, right, you won't maintain like an accurate threshold for monitoring your risk of your loan. The other one is that we don't, because the blockchain is trustless and it's kind of hard to kind of go and like store like credit scores in like a centralized contract or something like that. We actually don't have a lot of really good solutions for kind of creating some sort of like credit scoring or like reliability scoring on chain. There's a lot of teams working on this. It's actually one of the areas that I've been looking into at Polychain. So please feel free to reach out if that's something you're interested in learning more about. But there's a lot of problems where yes, you could technically go set up a smart contract that'll kind of have access to whether or not, or could integrate with other protocols and see like whether specific addresses kind of paid back their like deposits or like their collateral on time. But that information will be public, and that's obviously some information you won't want to be public. So until we figure that out, we'll need to have kind of loans or borrowing that's very like highly secured and over collateralized, so there's more money that you're putting into to take out. There's additional risk in DeFi. Oh, sorry. There's additional risk in DeFi that comes from kind of composability and smart contracts. So one really interesting thing about DeFi is that it's kind of called Lego blocks of money, where everything is kind of represented as a token. So when I go and I lend out money, right, for example, to Compound, I actually get a token in return that represents kind of my share of a pool. So if I go and lend out Ethereum to Compound, I'll actually get something called like CETH, which represents my share of that Ethereum pool that's being then lent out to other people. And because that's a token that I can use as money in and of itself, I can actually go and like, then use that for like Uniswap to go exchange in like a pool, right? So as you can see, it can like really build up really fast because everything is represented as tokens that can be represented, that can be used in other protocols. So that kind of creates this composability risk where it's like, if you have really kind of complex interactions between all of these, if one of them goes down, it can have like really kind of widespread overarching kind of effects. So just something to always keep in mind. And obviously smart contracts can always get hacked for value. So always important to make sure your contracts are secured and audited. And finally, this one's a little bit of a trickier one to kind of wrap your head around, but a really important kind of front of mind issue now is that people can actually quote unquote like front run you in the mempool. And what that essentially means is like, if I want to go, say exchange like a ETH again for Bitcoin in Uniswap, and there's a certain price depending on like the proportion of the two currencies in that pool. Someone can go look at transaction before it's confirmed. So when that transaction is in the mempool, right, where it's like waiting to be collected and verified, can actually submit a transaction that's the exact same or like at certain tweaked values with a higher gas cost, right? So that when it has a higher gas cost, miners are going to want to take that one first because it means they'll get more rewards. And then that might go and change the proportion of the pool. And then the initial kind of order I put on, I may end up paying more than I would have if that person hadn't seen my transaction and gone and submitted a transaction before me. So that's another thing. Yeah. And I'll leave you guys to think if you can think of any kind of other potential issues with how this might be architected. So another one is prediction markets, and you may have heard of these in kind of real world. The one image we have kind of up is Predicted, which is a kind of a real world prediction market where people can go and bet on like political outcomes, right? So an example is like who won the 2020 presidential election, Trump or Biden. Thing with Predicted though is like it limits you at 500 and it's highly regulated. So one interesting use case in terms of blockchain has been kind of developing prediction markets on chain where people can go and actually bet on outcomes. And the idea here is to draw on the wisdom of the crowd. If you can create a market based on like a certain topic, like, was movie X like good or bad, right? And you see that like the share that represents kind of good is like trading for 65 cents and the share that represents bad is trading for 35 cents, then you kind of know that like 65% of people think that movie was good or 35% think it was bad, right? So that's what this is. People bets are replaced with shares of outcomes. And the way this works is like if I have a market, usually most markets work like this, and I want to like go and buy like, or if I want to go create like a set of outcomes. So say like my market, my question can only have two answers, yes or no, right? um, I can actually go and mint shares where it's like I'll give the protocol $1 and it'll give me a share that represents yes and a share that represents no. And then the market will decide what those kind of sum up to, each of those individual shares. And if I take a yes share and a no share and I sum their price, it'll always equal to $1. So that's how you can kind of trade. It's like think of it as a kind of like a stock market for like outcomes instead of prices. And then we'll have oracles, like we mentioned, external data sources come and report on the outcome. So why do we actually care about even having prediction markets on chain, right? Like why can't we just stick with predicted or even stick with, you can think of stock market itself, or you can think of sports betting markets as prediction markets in and of themselves with a very kind of niche application. The one thing that we really kind of want to make sure is that we have prediction markets that don't crash and they're completely transparent, right? We want to have markets where like everyone can see what's going on, so no one's actually kind of rigging the market, right? And no one's kind of manipulating outcomes for their own benefit. So that's kind of one advantage you get when you place it on Ethereum. A few others kind of are there's no restrictions on market types. Liquidity, people can go and a lot of people can go participate freely. So there's a lot of kind of liquidity, which means you can like trade your stuff really easy on the platform. It's censorship resistant, which we'll get into, but basically there's no like restrictions on like markets that can be made and whatnot again. And it's automated and trustless. Again, you're not relying on some organization to like actually go and like settle the outcome and like do the payouts. It's all going to be handled programmatically on chain with very kind of complex cryptoeconomic cryptoeconomic mechanisms for ensuring that accurate info is reported and that markets are resolved correctly. So just some example use cases of prediction markets, right? Like I can go buy information, like again, will movie X flop or not before it happens? Like I can go issue a market, and then depending on like whether or not yes or no is like what price they are, I can just translate that directly to a percentage, right? So like 70% saying yes, it'll flop, 30% saying no, then I'm going to say that people generally think that 70% of people would are going to think it's going to flop. Hedging and insurance, in terms of hedging and insurance, right? Like say I have like a house, right? This is an extreme example, probably won't happen in the wild, but I'm worried that it's going to be burned by the kind of the California wildfires. One way I could kind of insure against that is like go and create like a market of whether or not my house will burn down, and just go buy like a bunch of like yes or no shares depending on what it is, and then get the payout, right? And there's a few other ones, right? Like you can go and like create a market on something as simple as like, does my smart contract have a bug? And if I think a lot of people say yes, then like there's probably a reason to go take a look at my smart contract, or there's probably a reason, or there's probably like incentive for those people who said yes to go and try and attempt like a hack on the contract, or like do a white collar hack or white hat hack. Sorry. Yeah. But this gets into the kind of the censorship stuff. So one thing that's kind of been tough to crack with prediction markets, and one reason that you always got to be careful with them, and make sure that there's only you're using the right platforms, is because they're censorship resistant. They can also have some pretty dark markets, right? So the kind of prime example of this is like an assassination market, where you say like I bet this much, or like I want to issue a market of whether or not Bob will be alive on like October 4th, right? And I might just go and buy a bunch of no shares because everyone's betting yes, and then go and try and assassinate Bob myself, right? So there's always kind of like a danger of when you get into some less savory use cases that an individual could have kind of real world impact over, and the consequences could be really disastrous in terms of someone dying or getting hurt or something like that. That will arise. We haven't seen as many assassination markets on kind of the main platforms, which are like Polymarket, Augur, and Gnosis, but they're always a concern. So it's kind of one of those risks that it's really difficult to kind of hedge out of your system. Yep. So
That's all we have today. Well, yeah, thank you everyone for joining us today. If you have any questions, feel free to just link in the Q&A. We'll stick around for a bit, but that's all we have for today. So thank you.
okay, I think Steve asked if prediction markets are a type of legalized bookmaking. You can think of it sort of as that. The main thing I would say is like there's different kind of flavors for prediction markets. Bookmaking is like when I maintain kind of a book of like who wants to buy this share and who will like sell for this share. So yes, there's like prediction markets that do work like that, like Augur and Polymarket do work like that. But the person actually making the books, it's an on-chain kind of smart contract. So it's doing it algorithmically. There's no kind of central entity, or they're distributing that bookmaking across like a lot of different people. So and securing them through some sort of like crypto economic mechanism. And they're legalized because the shares of these markets are actually issued as kind of Ethereum ERC20 tokens or ERC. I think they use like another standard ERC 755 or 1155. So they issued those as Ethereum tokens, and Ethereum tokens aren't kind of classified as securities, and they don't fall under kind of current kind of gambling law, right, or betting law, right. So that enables them to be legalized. So it allows you to like trade those outcomes on chain. They'll have their own inherent value again. So because those are tokens, I can actually go and like even lend out like the token representing the outcome of that market to someone else using like another protocol.